So if you are just joining us, or if you joined us after I got rid of it, I'm not going to rate all the words, but we're going to talk through what the situation was. So I said that we have a tank, and our tank holds 500 liters of liquid. And into that 500 liters, there are 400 grams of dissolved lemon juice. And we're trying to make some lemonade. I have no idea how many grams of lemon juice we should put in 500 liters. I've never made 500 liters of lemonade, so I just made the numbers up. So that's our situation. And what we're going to do is pump into the tank pure water. And that water is flowing in at a rate of 100 liters per minute. And then it says that the well-stirred mixture is flowing out at the same rate. So at the same rate, I've got the mixture that's flowing at 100 liters per minute. Now I'm putting all of the units down here because for me, the easiest way to think through these tank problems is to start with the units, make sure our units work, and then get rid of them and just do the math. What I've asked us to do for the first part is to write a differential equation to model the rate of change in the amount, A, of lemon juice concentrate in grams per minute. Now I should have said that this right here, this is what we have when T equals 0. I've got 500 liters in the tank and 400 grams of lemon juice concentrate, which I'm choosing to call A. So just to remind myself off to the side, so A is the amount of lemon juice in the tank at any time. So what we know in this problem is that I've got stuff coming in and stuff leaving. So in general, that differential equation is going to say the rate of change for the amount of lemon juice in the tank is going to be the amount that came in minus stuff out. Now I mentioned that I like to work with units here. So the units that we're going to have for AATC, this should look like grams per minute. So anything that I have on the right-hand side also needs to have units of grams per minute. And I don't want that to look like grams per meter, so I'm going to write out MIN for minutes. Well, in terms of what's coming in, I know the rate that it's coming in is 100 liters per minute. These units don't work. I need to multiply this by something that has units of grams per liter in order for those liters to cancel out and to have the same units on both sides. So if we're thinking about this, because it's pure water, how many grams of lemon juice do we expect to be in pure water? Thank you for the person who wrote it in the chat. I would expect there to be 0 grams of lemon juice in water coming out of my tap. I expect no grams of lemon juice to be in the pure water that's flowing into the tank. Now for the stuff that's coming out, again, I know that it's coming out at 100 liters per minute. And in order for my units to work out, I'm going to have to multiply that by something with units of grams per liter. Now this right here, this is the critical step in every single tank problem. This part is flowing out of the tank. And if it's flowing out of the tank, then the number of grams of lemon juice that are in the tank is A, because A represents the amount of lemon juice in the tank. So I have A grams of lemon juice. Now in terms of liters, again, it's flowing out of the tank. and my tank has 500 liters in it. After I've made sure all of my units work, then I get rid of the units so we can just focus on the math. So this would look like dA dt is equal to, well, 100 times 0 is 0. So I'll have 0 minus, over here, I'll have 100A divided by 500. Or if you want, we could just write that as -1/5 A. So that's our differential equation, and that's the thing that we need to solve. This thing happens to be autonomous, because when I look at the variable that's in the numerator of my differential, that's the only variable that appears on the other side of the equation. So I know it's autonomous, therefore it must be separable. I think I can address the question in the chat of, do you have to show the stuff in minus stuff out? I would say that if what's coming in is something like pure water or fresh water, something where it's going to be 0, you could start on this step and be fine and get full credit. If what's coming in does not have a concentration of 0, then you definitely need to write that part out. This top line is just for us. I probably wouldn't write that on the test. It wouldn't be wrong. You could write it on the test. But if what's coming in is really 0 in terms of the concentration, you don't have to write this step out either. You can go straight to here. If I'm going to solve it, we have choices, which always makes students uncomfortable. But I like to leave the number part alone on the right-hand side when I'm separating the variables. So when I rearrange this, I'm going to go ahead and I'm just going to give myself a nice clean line down here, -1/5 A. So I'm going to multiply both sides by dt. And I'm going to divide both sides by A. When I do that and clean it up on the left-hand side, I'm left with 1/A dA is equal to -1/5 dt. And both of those are ready to integrate. I don't need to use substitutions or anything fancy. I'm just going to go for it. When I integrate 1/A with respect to A, I get natural log absolute value of A. When I integrate -1/5 with respect to t, I'll get -1/5 t plus a constant. Oh, by the way, sorry, I should have paused here, but that answered part A of my question. And now I've moved on to part B, which asked us to solve the differential equation. Going from here, to get that A by itself, I'm going to take this log expression and rewrite it in its exponential form. Or you can think about it as taking both sides and raising e to all the stuff. So I'll be left with A is equal to e to the -1/5 t plus a constant. This is again a place where we have choices. We could solve for this constant now. Mathematically, we typically don't. Instead, we rewrite this because there was really an absolute value on that A. So for being mathematically precise, we would have a plus or minus in terms of that part. But the way we handle that typically is to rewrite this right-hand side to think of that as e to the -1/5 t times e to the c, and then make that whole thing a new constant. That way the constant itself can take on either a positive or negative value, depending on what our initial condition is. So this right here is almost my solution to the differential equation, but we need to take our initial condition into account to solve for that constant b. So I'm going to erase this, get myself just a little more space in here to say, so right now what we've got is A is equal to B e to the -1/5 t. And if I look at this initial condition, I know that A should be 400 when T is 0. Just another place that if you're rushing on a test, don't make the mistake. E raised to the 0 power is 1, not 0, which means B is 400. So my final answer here would look like A of T is equal to 400 e to the negative 1/5 T. And I kind of lost the top of my 5, but hopefully that's readable. The other piece that I asked in this question, so I asked us to solve the differential equation and find the time it takes for the concentration of lemon juice to be half of its original amount. Well, if the concentration is going to be half of the original amount, then rather than having 400 grams of dissolved lemon juice, actually, I don't know, yeah, I'll use the phrase dissolved and a chemist can tell me I'm wrong, but of dissolved lemon juice, if we're going to be at half that concentration, the value would be 200. So I would need to plug in 200 for A, and then do algebra to figure out T. By the way, the algebra we're about to do is exactly the same algebra we would do if we were finding half-life, because essentially what this is saying is the amount of lemon juice in the tank is a decreasing exponential function, and we are looking for when we're going to reach half of the original amount. We don't really call it half-life, but it's the same set of algebra that we would do if it was a half-life problem. Now, there's a question in the chat that I don't want to ignore. So if this was not the condition at time t equals 0, but maybe this was the condition at time t equals 1 or 7 or 5, then when we solve for B, we'd have some ugliness to drag around with us. And there's definitely a web work problem where that's going to happen. So if this weren't a 0 and this were instead like 6, then B would equal to 400 divided by this whole thing, the e to the negative 1/5 times 6. It's going to be messy to type into web work, but it's the same sort of process. It's just an uglier constant. I'm going to go ahead and do the algebra here to solve for T, but I kind of need the space. So I'm going to erase my differential, but I'll just erase the picture. We don't really need the picture anymore. So to work through this algebra, I've got 200 is equal to 400 e to the negative 1/5 T. And if you have friends or cousins or younger siblings that are still in high school, give them the advice. The algebra is the trickiest part of calculus. Tell them to pay attention in their algebra class. Okay, back to this. The reason that we've set A to be 200 is because the question that I asked in my warm-up problem was to find the time when the amount in the tank was when the amount of lemon juice was half of the original amount. So it was part of the statement of the problem. That's why we're setting it equal to 200. So in terms of the algebra here, I'm going to divide both sides by 400. So 200 divided by 400 would give me 1/2. And I've got e to the negative 1/5 T. So I'll take the natural log of both sides. ln of 1/2 is equal to negative 1/5 T. And then I'm going to leave my T as natural log of 1/2 divided by negative 1/5. And even if we're thinking about doing this like in the context of a web work problem, I would type this in personally. I wouldn't put it into a calculator. WebWorks sometimes is picky about how you round numbers. So if I don't need to round, I would just type it in like that. And the first thing that I want to do is to just write down the differential equation that goes with these words. So there are a couple of vocabulary words that are hidden in this problem. that I want to talk through, just in case they come up on worksheets or tests or the test on Friday. So per capita means 1/n. It means that whatever the thing is that we were adding up, we're dividing it by the number in the population. So you may have seen per capita COVID testing rates. It's a phrase that gets talked a lot about in data. California has one of the highest per capita vaccination rates at the moment, which means relative to the size of the population, California has a lot of people vaccinated, right? Or I don't actually know that we're the highest per capita, I made that up. But that's what it would mean, is relative to the population. So when it says per capita, we write 1/n. Growth rate is telling me this means write some kind of differential equation, meaning I'm going to write dn dt. So taken together, the per capita growth rate means 1/n times dn dt. The next part here is that it says that our per capita growth rate for the population is proportional to. And is proportional to means the same thing it did in like integrated 2 or an algebra 2 class. That is proportional to means equals some constant times. Now, if it said inversely proportional to, then it would be a constant divided by. But is proportional to means the constant times. Now, the thing in this case that we are proportional to is the square of the population, meaning take my population and square it. So we've taken this word problem and translated it into a differential equation. Just for funsies, let's go ahead and solve our differential equation that we just wrote. Well, the first thing that I'm going to do looking at this differential equation is to say I have a differential part. I'm going to multiply both sides by dt. Well, I've got 1/n dn on this side. Oh, but I still have n's on the side with my dt, which means before we can integrate, I still have to finish separating by dividing both sides by n squared. On the left-hand side, kind of cleaning up that algebra, I already had a 1/n. So if I divide by another n squared, that'll be 1/n cubed dn. And over here, I'd have that constant times dt. Now we're ready. I can take the integral of both sides. On the left-hand side, we probably are better off thinking about n cubed, 1/n cubed as n to the -3. So when we add 1 to the exponent, we'll be at n to the -2, and then dividing by the new exponent. So I'd have n to the -2 divided by -2. And that whole thing would be equal to kt plus c. We could keep going and solve this to make it say n equals, but the thing that I really wanted to practice was just writing the differential equation from the word description. Are there questions about that step? Because what I want to do now is lead into taking a look at question 2 on worksheet 7. But I'll pause for a second in case there are questions about this in particular. Not seeing questions pop up. So I'm going to go ahead and pull up worksheet 7 and take a look at problem 2. There's a whole lot of words in problem 2. But essentially, the first thing that we are being asked to do is to write down that differential equation based on the words. So we are told that according to Newton's law of cooling, if an object at temperature T is immersed in a medium having the constant temperature M, then the rate of change T is proportional to the difference of temperature M minus T. Just going to take that last part of that and write it out. So it tells us that the rate of change in temperature T is proportional to the difference in temperature M minus T. Now, Newton's law of cooling gets written with a lot of different letters involved. This is a particular set of letters from worksheet 7. There's another Newton's law of cooling problem in the web work homework that uses different letters. They don't use M, but the idea is the same, the rate of change. Okay, so if we kind of dissect the words in the same way here, rate of change means write a derivative. I'm going to have dd, dt, dt, d big T, d little t. So that top T, I'm just reminding myself, that's the temperature. That one is time. Same thing as that previous problem, is proportional to means we write equals a constant times. And then the thing that we've been told it's proportional to is the difference in temperature M minus T. So I'd have M minus T. Now there are a couple of things that are important about this. In terms of the context of the problem, we are told that M is the temperature of the medium. Now that's kind of a weird way to phrase it. This means the temperature, sometimes we also think about it as the temperature of the surroundings. So when I poured myself this glass of water, I took it from the fridge. So it was colder than the temperature of this room. But if I leave it in here long enough, we expect both the glass and the water to eventually be at the temperature of the room. If you left everything in here long enough, we would expect, and the temperature of my room was constant, which is not, it heats up in the afternoon for sure. But if we pretend that the room had a constant temperature, eventually we would assume that everything in the room would be that temperature. Now there's a question in the chat about will there always be a constant times the rate? So this phrase is proportional to means there is a constant in there for sure. If this just said the rate of change in temperature T is equal to, then we would not write the constant. It's specifically the phrase proportional to that tells us we need to include an additional constant in here. In terms of this differential equation, we're making the assumption that the temperature of the medium is constant. And that's actually really important for Newton's law of cooling, and it's one of the underlying assumptions in Newton's law of cooling. The next part of this question asks us to solve this differential equation for T. But I was also asked to do some problems that are kind of like question 1 on the web work. So I'm going to change this up a little bit and give us actual constants for K and M before we solve it. So, okay, there's like a flurry of questions, so let me address those before I move on. The constant would also be there if this said is inversely proportional to, then if that were the case, then this equation would say dt is equal to a constant divided by m minus t. That's what it would look like if it said inversely proportional to. By the way, I don't think I've seen Professor Chaudhuri do one that said inversely proportional to. I could be wrong. I might have missed it. Next question on there is Newton's law of cooling on the exam. So here's what I would say, potentially, right? So in the things that you are supposed to study for short test 3, that includes worksheet 7, which has Newton's law of cooling, and web work homework 6, which also has Newton's law of cooling. So I would say, yes, it's potentially on there. If it's on there, I don't think that he is expecting you to like have memorized a formula for it, though you could certainly put it on your sheet of notes. I do think what he's expecting is that you can take this statement about the rate of change and write the differential equation from it. I think that's the important skill that is likely to be tested. I know that this is autonomous and therefore it's separable. What I'm going to try to do to solve this is start by multiplying both sides by dt, recognizing that then on the right-hand side, I'd have y's and t's. So I'm going to need to divide by my term with y's in it. Whenever we're trying to do this separation of variables thing, it is important that we're always multiplying or dividing to move things from one side of the equation to the other. If you find yourself adding or subtracting, something has probably gone wrong. To clean this up and write it a little more neatly, we've got 1 over 4 minus y dy. And on the right-hand side, I've got 2 dt. Both sides are ready to integrate. On the left-hand side, even though it looks like, oh, hey, that's just a natural log, I know what's going to happen. It's not quite a natural log. It's going to be a negative natural log. And the reason is that if we take a minute to write out the u substitution, u would be 4 minus y, which would make du negative dy. Oops. Because the derivative of 4 minus y is like -1. So I'm going to have it negative dy, which means that when we rewrite this from u sub, we end up with negative 1 over u du. Then I'm ready to integrate, end up with negative natural log absolute value of u, which is going to turn back into negative natural log absolute value of 4 minus y. On the right-hand side, if we integrate 2 with respect to t, we should get 2t plus a constant. I want to go ahead and work through the algebra on this one to get the y by itself. And the first thing that I'm going to do before I write it up there is I'm going to multiply both sides by -1, because I'd like to have this say natural log of something equals, so we can do the e to the stuff on both sides. So if I multiply both sides by a -1, that looks like I'm doing it as an exponent of -1. I don't like that. Hold on. -1. Then I should get natural log absolute value 4 minus y is equal to -2t minus c. Again, we have all kinds of choices with what we're going to do over here, but the most common choice is to write this as e to the -2t times e to the c, and then rewrite this as a new constant. I would end up with 4 minus y is equal to b e to the -2t. So if I want to get the y by itself, I can add y to both sides. and subtract BE to the negative 2t. So I'll end up with 4 minus BE to the negative 2t is equal to y, which would be enough if we were finding the general solution. But on the web work problems, you're also given an initial condition. For me, on the first part of this web work problem, it was given an initial condition that includes time being 0. On the second problem, it was given an initial condition where they're both numbers. So let's do one where they're both numbers. So maybe I might write this as y of 1 is equal to 5. Well, if y of 1 is equal to 5, that means I'm plugging in 5 for y and 1 for t. So I'd have 4 minus BE to the negative 2. It's not pretty, but I can subtract 4 from both sides. Okay, that part's not too bad. So if I subtract 4 from both sides, I'm left with a 1, and then I'll divide by negative e to the negative 2 and get b equals negative 1 over e to the negative 2. And this, I'm going to be clever and rewrite as negative e squared. We don't have to do that step. I just think it's a little bit easier if I had to type this into WebWork instead of this. We're not done because we now have to take that constant and plug it back in right here for b to get a final answer that looks like y equals some stuff. I'll punch a hole right here to put my final answer of y equals 4 minus, and b I wrote as negative e squared, and then we've got e to the negative 2. So minus a minus, I could make that a plus and have 4 plus, I lost my t, e to the 2 times e to the negative 2t. At least sort of okay. But I wanted to talk through kind of what I was looking at for these slope fields. So what the very first thing that I try to find when I'm looking at the picture for a slope field is I always look for a place or places where it looks like the slope is flat or a slope of 0. So if I look at, for my picture for A, the flat slopes aren't actually drawn in, but I can kind of tell that in here, the slopes from above are flattening out and the slopes from below are also flattening out. So even though it doesn't show me the place where the slopes are 0, I can kind of imagine that it's in there. If I look at D, it is very clear where the slopes are 0. And C is just a hot mess. There are things going around at every angle. B, I'm not seeing a whole lot of places where the slope is 0. I see one particular point where the slope is 0, but that's kind of it. But those two that I have so far might be enough for me to eliminate some of the options. So then I come up and I look at the equations and I think about, for these equations, what would it look like if I tried to set the slope equal to 0? And I always start with the one that looks the simplest. And if y prime is equal to 2y minus 2, then if I set that equal to 0 and factor a 2 out, then I would have y minus 1. So that tells me that whenever y equals 1, I expect to have a slope of 0. Well, that's going to match with set A, because everywhere for y equals 1, my slopes are approaching 0. For D, what I can tell here is the slopes are 0 everywhere on the y-axis. Well, the equation of the y-axis is x equals 0. So now I'm going to look at the equations and find if x was equal to 0 in any of these equations, would I get 0 for y prime? And equation 2 for me is the one that's going to do that. So for equation 2, if I plugged in 0 for x, the whole thing would go to 0. So figured out D. So now I'm down to B and C, kind of process of elimination here. And I didn't have a great way to necessarily figure out the B and C, but what I'll be real honest, I looked at C and I was like, oh, stuff's squiggling all over the place. That's probably the one with the trig. That is genuinely what I did, which process of elimination told me what B should be equal to. But if I look at B, then, and try to reason through it a little bit more. So I did identify this one place where it looks like the slope is 0. And so if I think about that equation, this wasn't perfect, and it was a little bit hard to see what might be happening there. I couldn't quite figure out like what point exactly to plug in. So instead, I went a different route, and I looked at that equation and I said, well, what if x is equal to 0? Because that would make the whole equation look more simple. And if x were equal to 0, then y prime would just be y plus 1. And if that's the case, then I can just look along the y-axis and see if those slopes kind of make sense. So if I look at the slopes along the y-axis, it does look like the slopes are pretty flat in here near y equals -1. And above the line y equals -1, they all have positive slopes, which makes sense given this equation. And below the line, and below y equals -1, they all have negative slopes, which again works with the equation. So we figured out what goes there. This one was just a hot mess. So to back up to how I figured out D, I knew that everywhere on x equals 0, the slopes had to be 0. So I just looked at the equations and I plugged in 0 for x to see which one would immediately be 0.